do that.
Okay. We can upload it in the break, maybe.
Yeah, I can upload it during class.
Oh, okay. Yeah, it's inside the SharePoint folder. So. All right.
Good morning. Good morning. This one more. This one more. Just speak into the one.
Right. Technical difficulties.
Actually, works fairly well. All right. Good morning, everyone. Good to see you again. So today I have the pleasure to introduce you Ian, who's a second-year PhD student. Do I have that right? And he's working on load shedding for data processing systems. So he's quite comfortable with this area, not to say he's an expert. And so today you really have a privilege to hear from Ian on the subject. And yeah, so an announcement before we start. So this week we're releasing coursework 2, and that's going to be really important for the exam. So I really recommend you give that a shot. The practicals are running as usual, so there'll be a team of demonstrators there to help you out. And yeah, maybe one of us will be there as well to give you an extra pair of hands if you need so. So yeah, Ian, it's a pleasure to have you here, and please take it away. The floor is all yours.
Thank you, Pedro. So welcome, everybody. Today we're going to talk about routing, or routing, depending on your pronunciation. And I'd like to give credit to Dr. Arma Cantu and Dr. Dan Nesbitt for some of the assistance on the slide material. So what is routing? Routing is a series of algorithms that are responsible for determining which line in a network a series of packets takes to reach one machine to another machine. There's two distinct phases. We have the routing algorithm phase, and then we have the sort of forwarding phase right here. And in the algorithm phase, we make decisions about what the best strategy is, what the best path is through a network for our packets. And in the forwarding phase, we actually send those packets through the network. So most hosts have multiple outbound lines. You'll have lines that come into your machine for data to come through, and you have bounds that go out, right? So you can send data from those. And with a routing algorithm, we need to make the best decision about which one to pick at any particular stage in our network. So that could be from the first node in the network to the last node, or it could be a more localized process of looking at one particular node and selecting amongst the outbound lines for that node. And this really depends upon a series of factors right here. So we have speed of interconnections between our nodes. So that's looking at things like bandwidth, least hop distance, things like that. We have the parent load of the target host. So you might imagine, for example, in the case of something like Twitter or Facebook, where we have a lot of network traffic, we wouldn't want to send our data packets to a node that's overburdened. So that has a lot of traffic. For instance, there might be a node down in London, there might be a node up here in the northeast. The northeast node probably has less traffic than the node down in London. So if we could avoid that when trying to communicate with whatever centralized database or shard of database we're looking at, that would be useful, right? And lastly, just congestion. So we're going to talk a little bit more about congestion later in the lecture, but just sort of avoiding places, yet again, where we have a lot of data that's clogging up a pipeline, and it's sort of causing this process called back pressure, where it pushes pressure back up the system. So the selection of any particular route depends on a performance criterion. It's very vague, I know, but we're going to get into the specifics of that later on. And the simplest criteria we can pick, right, the easiest thing is it's called least hop distance. So logically in a network, I think we've talked about this before, you can separate the sort of physical infrastructure of a network, looking at a map across the world, into a series of vertices and edges, so nodes and links. And the least hop distance and the minimum hop distance would just be the fewest number of nodes we can pass through in order to send our packet from point A to point B. So how can we minimize the intermediary nodes? In the case where we have two links that sort of follow that paradigm, where we have just, so for instance, one hop in the middle, we pick the route that has the minimum performance criterion. So whether that be, latency or whatever. So routing algorithms can sort of be broken into two classifications. We have adaptive routing algorithms, or dynamic is what I refer to them as. And those are algorithms that look at the state of the network and how it changes, and update the criterion based on what's actually happening. And as you'd imagine, this is advantageous because networks are live things. You have shards or nodes within a network that go down. You have ones where the connection might get a bit fuzzy. Maybe a satellite passes out of orbit and you lose your internet connection to that. Or somebody's digging a pipeline and they accidentally cut through the physical wired connection. And you need to be able to make adjustments to how you make these routing choices depending on how your network has reacted. So the advantages, right, we've already talked about the advantages for that. The disadvantages, right, would be in a network where the performance criterion for your routing selection changes rapidly. So for instance, looking at congestion, that could change very quickly. If a particular node allocates more resources and it can handle more pieces of information, then you might want to push more data down that particular route rather than an underburdened route that has a slower connection. But if this changes a lot, if the fluctuations are quick, then what we're going to get is a bunch of different routing changes very quickly. And we call that overhead. So where the actual decisions about how we choose the route in our network change, and the actual, It's the increase in network packets that change the routes will cause a burden to the network itself, right? We don't want to do that. We don't have to send all these network packets and clog up our network. So sometimes it's better to select a non-adaptive algorithm. We call that static, where you make all these decisions up front or ahead of time based on, yet again, some selection criterion. And then we ignore any changes to the network. And you might think, well, that sounds silly. Why wouldn't I pick the adaptive version? The answer is, well, often, yet again, these fluctuations tend to be temporary, right? They might be when people wake up in the morning and they access a particular app and you get a bunch of requests at once. That will ease off very quickly, and there's really no need to have to change the routes we've already established. So a static algorithm would be a better way to select your routes in that case. Let's go back to the fixed route strategy. We represent our nodes as nodes in a graph, and we put them into a table where we it's a loud whining noise. We put them into a table where each node has its outgoing connections listed in the table. And the sort of advantage of this is you can hold all of the information about a network in a sort of a centrally located matrix or table, graph, CSV, whatever sort of temporary data structure you want to use. And this works really well for reliable networks with steady traffic, or networks where the traffic fluctuates, but we know that it'll dissipate quickly. Last line there, there's really no difference here between a datagram strategy and a virtual circuit approach. I think we'll talk about VCA in the future, but that's just for anybody who wants to look that up. Yeah. So how do we propagate the information about latencies between nodes, which node's the best one to select? You know, if I'm node B in a graph and I need to get to node G and it's all the way over here, how do I know what the best route is for that? And this is where flooding comes in. Well, one of the ways we could do that is what's called flooding. And this is where every node in the network sends a flooding message to every other one of its neighbors. And it tells them, hey, I am node B, for instance. Here's the information I know about the nodes behind me. I'd like to get information about the nodes ahead of me, please. And when the first node sends out that message to all of its neighbors will respond in kind, sending the message out to its neighbors, and its neighbors, and its neighbors, so on and so forth. So you can sort of watch it propagate through a network, starting from one place and going outwards. And what this allows us to do is very quickly identify all the nodes in the network, as well as the immediate cost information from one node to the next node. And eventually, after all possible routes are tried, we will find the shortest path eventually. Now, some of you might recognize the downside of this, right? We have to sort of waste a lot of computational power querying every possible node in the network, and we have the nodes to make decisions about which nodes have previously been hit and which nodes haven't been hit, and there's a little bit of overhead there. So we have other ways of sort of dealing with this problem, one of which is random routing, which, as you'd imagine, is the process of randomly selecting an outgoing node and querying that node. So there's not a lot of logic there, so a lot less overhead in terms of sort of computational overhead. Yeah, a lot less resources. But the only downside of this, right, is it is sort of random. You can weigh the probability of which node is selected in this randomness, which can sort of, if you know the topology of your network, or you know the specifics of what the nodes in your network are and how you want to query them, this can sort of weigh the effectiveness of your random routing algorithm. But at the same time, it's not the best strategy to find the best possible path quickly. It will eventually get there. If you have sort of n number of nodes, you will eventually get there in big O of n. So now we get to the thing people actually use in real life networks. As you'd imagine, flooding and random routing was sort of a precursor. This was a thing back in the 60s and 70s. And I think about that time, people invented link state routing, which is the big boy. So in link state routing, LSR, if you see that, that's the link state routing, was sort of 5 distinct points to this algorithm. We discover all of the neighbors in our network and learn their addresses. We store those locally within our node for future queries. We then measure the delay between our node and all of our neighbor nodes. This decision, yet again, is based on performance criterion, whether we're looking at latency, congestion, whatever it might be. So whatever that measurement is, we store that. We construct a packet, which is just a unified way of representing that information for all of our neighbor nodes to let everyone else know, hey, here's what I've learned from my local query. And then we distribute that packet to all of our neighbor nodes. And yet again, there's sort of a bit of redundant information in there, right, between our node and our neighbor node. Our neighbor node will know what the latency is or whatever the criterion is for that link, but it won't know for the links from the original node to all of its neighbors, right? So this is useful to sort of propagate that information through our network in a way that's slightly more efficient than flooding or random routing. And then lastly, once all of our nodes in our network have this information, we sort of shared it with each other, we can use that to compute the best route through our system using something like minimum delay. And we can, the really cool thing about this is we can use a static algorithm, so something that doesn't need to know the live information about each node in the network, because yet again, that's a lot of overhead. So we sort of run this process periodically. That's up to the sysadmin of your network, or the sort of agreed upon process between the people who manage your nodes. And as long as we run it at regular intervals, we can update our network to respond to big fluctuations, right? So the small stuff, the stuff that changes quickly, we don't necessarily care about. But say 50,000 new users at a company come online, and there's a lot of information coming from a particular node, we might want to change our routing preference around that node, right? So let's go through the process together. So the first point, we discover our neighbors. So we have a node A right here, and we want to let node B know, hey, I'm A, you are my neighbor. So we pass along our network address as well, just so that it can use that in stage 2 and 3 to store that in its table. And in stage 2, now we've established, right, I'm node A, node B exists as my neighbor. I'm going to send a packet to node B, asking it to send me a packet back so I can measure the latency between us. And usually this process is very low latency. It's sort of a bang-bang situation, and that's because we're going to measure whatever sort of latency criterion we have between our two nodes. So this is the bit that gets slightly complicated, but it's not that bad as well. So for each node in the network, A, B, E, etc., we construct a routing table of all possible edges. So this sort of complicated graph on the left, just look at node A. And then you can look at the node A routing table to the right. Node A only has 2 neighbors. It has neighbors E and B. So we put those 2 neighbors within our routing table. And then we put the associated measurement that we got from step 2 next to it inside of our routing table. So here, let's pretend this is latency in milliseconds, right? Let's just assign some sort of unit to make sense of it in our heads. And we put down, OK, B has a latency of 4, and E has a latency of 5. And when you look at sequence and age, that's just to keep track of when a routing table was constructed in relation to other routing tables and how old that routing table is. So around that decision of when should we make our update, well, we store how old it is in our actual little routing table. And then if it ages out, it hits some timeout period, we rerun our algorithm, the first 2 steps of link state routing, in order to update the values in our table. So that's that. And then the same thing for each other node within the graph, right? We have B, C, D, E, F. And as you know, there is some redundant information here, right? In between nodes. So 4th bit, I don't have a nice picture for this, but we distribute these routing tables. So for instance, node A knows the routing table for itself, right? It knows the information about B and E, but we need to distribute that to the other nodes in the graph. So we sort of send this out. It can be in a very similar process to step 1 of link state routing, where we just transmit between 2 nodes. So we select our best neighbor and send it to them, and then that will disseminate. Or we could do something like flooding, where we say, hey, here's a packet full of all of my neighbors and the connections. I'm going to send that out to everyone. Depends on how the network admin set things up. And then lastly, once everybody has access to everybody else's routing tables, we can run an algorithm using that information in each localized node to figure out, OK, what's the shortest path? What's the best way to get through it? And sort of one of the best algorithms for that is called the shortest path algorithm, or Dijkstra's algorithm. I believe Dutch computer scientist and mathematician. Yeah. And this is my favorite algorithm in computer science, so hopefully I can walk you through this. So this is Dijkstra's algorithm. OK. So this gets a little bit complicated. If anybody doesn't understand, please stop me, and I'll try and clarify. So we build a graph to represent our subnet, right? And this could be massive nodes at a global scale between China, India, the United States, the UK, Germany, right? Or it could be within the USB, right? We have one node here, we have one node there, we have one node across campus and main campus, and how do we get data back and forth between them? So each node represents a router, which is sort of like a computer that exists to forward packets back and forth. I don't know if we've talked about this yet, but you have? OK, good. And then each arc in the graph, each edge in the graph, represents a line of communication, whether that be physical or over wireless. Using something like link state routing from the previous set of slides, we can find the cost distances for each link in our graph. Right? So we use link state routing to figure out the localized costs between two nodes, and then we can propagate that throughout the network. And now everyone has an idea of what the intermediate costs are between each other. And then, effectively, when we want to make a routing decision between a node A and some other node in the graph, we just select two nodes. We go, okay, here's the path I want to draw. And we use this algorithm to figure out what is the shortest path from A to G or something, right? And when there's only a few nodes, this is relatively trivial, especially if there's only two, well, there's only one selection, right? But if we have 3 or 4 nodes, perhaps if they're in sequence, it still might be trivial. You might only have one branch, and you just pick the one that has the least. But when we have 5, 6, 7, 8, 20, 30, 40, 50 nodes, this gets very complicated. And consequently, we rely on the maths of Mr. Dijkstra to solve this problem. Going back to the selection criterion, performance criterion bit from earlier, here's a couple of possibilities for performance criterion. So least number of hops. We could do the shortest geographical distance, because that does have an influence on physical cables, right? You can measure the queuing delay, so how long does it take to pass through a particular node within our network. So when we hit it and we hit the buffer, how long does it take until we go to the output buffer and get sent along in our network? You can measure the transmission delay, which again is sort of link state routing, LSR. Or we could, design some clever algorithm or heuristic that combines a bunch of these together. And that's a lot of what sort of PhD students and people doing research do, is they find better and better ways to combine these heuristics to achieve a more efficient network algorithm. And yet again, it's a sort of a static algorithm, so we need to run it several times in order to figure out what is the best path as things change. Eventually, following this algorithm, we're going to go into in a few slides, we will figure out the best path between all nodes within the network. So initially, we pretend that the distance between every single node in the network is infinity. So the worst possible case, right? It takes forever time to get from one node to the next node. And as we run the algorithm, we update the weights of each of these steps, how difficult it is to get from one node to the next node, to reflect their true value, or at least the localized value we have at that node. And as we propagate through the network, we'll figure out the true absolute value between any two nodes in the network, which allows us to figure out the best possible path. Okay? And yeah, we sort of label these decisions as tentative or permanent. Tentative being, I believe this is the best possible path, but I haven't yet looked at all the possible solutions. And permanent being, I've looked at all the possible solutions, this is definitely the best solution. So this is the algorithm. And I'm going to walk through with a couple of tools to sort of help us out. So starting out, we have a very, very simple network. I talked about it earlier. We only have 2 decisions. That's what we've done here. So we want to get from node A to node D. How do we make that decision? And we have the localized costs for each node in the graph, right? Using something like link state routing. So A knows the connection between A and B, and A and C. C knows, between itself A, B, D, etc. So following our algorithm, we select the first node, the node we want to transmit from, and we add that to a set for consideration. So A's been put into our set right here. And we then we add A into consideration, and we want to look at the weight of all of the neighbors for node A. So because A is where we're starting from, it's our start point, there's no initial weight, there's no initial cost to start from A, because we are node A at the beginning. It's sort of like saying, what's the cost of sending a message from your machine? Well, 0, it's your machine, right? Whereas, what's the cost of sending from a machine in a professor's office on the 6th floor? Well, you're going to have to climb a bunch of flights of stairs, and you can make a heuristic out of that, right, to figure out what the cost would be. So starting off with a current weight of 0, node A, we analyze all the neighbors of node A, which is going to be B and C. And then we put just the localized cost. So we're not totaling anything up yet. We're just going, okay, what's the intermediate cost from A to B, and then from A to C? And that's going to be 4 and 2. And from here, we can update our master routing table at the top to reflect what are the costs from A to B, A to C, and A to D. So from A to B, the cost is 4, and the starting point is node A, so that's why we do 4A. For B, it's 2, and then 2A. And then for D, there is no connection, so we leave it at that infinity state we talked about before. This sort of implies there is no connection, there's no possible way to get there, it would take forever for you to receive a connection between the two. So that's obviously not the best solution, we need to find a better one. This is where the sort of beauty of the algorithm comes in, because we can now remove A from consideration, and we know that there must be a better solution to D in our network, because D is connected to our network, than infinity. So there will be some other link that we can use to update this. And it's sort of a least cost scenario, right? Where we look at all these connections and we go, oh, are you less than the one we currently have? If you are, fantastic. We're going to update you within the table. So now, looking at those two, between A to B and A to C, A to B has a cost of 4, A to C has a cost of 2, 2 is less than 4. So we're going to move to node C and rerun the sort of step from node C. But just like with link state routing and flooding and all these other network bits, right, we already know the connection between A and C. So we're not going to look at the connection between A and C. We're just going to consider from C to B and then from C to D. And try and determine, are there any better routes we can take with that information? So we add, and because we've moved from A to C, we know that's the shortest connection from the start of our network to any point in our network C. So there isn't going to be a better one. So we go ahead and remove C from consideration here. Just add dashes. Just if you're doing computing, you set it to null or something, right? We're no longer going to consider that bit. So we put C into consideration for our current node. The current total to get to C is the link from A to C. So the total weight is going to be 2, which is that cost. And we look at the neighbors of C that haven't already been considered, which is B and D, and we add them into our neighbors table. And then yet again, we're looking at just the intermediate costs here. We're not looking at the total cost. So the cost from C to B is 1, and from C to D is 2. So we update that into our table. And now this is where the total cost comes into play. So the cost to get to C was 2. And the cost from C to B is 1, and to D is 2. So we update those values within our table. So you can see the prior cost of 2 here, and then the cost from C to B is 1. So we're going to update our table with 3. And this is sort of crucial. We only update the table if the current selection, so from C to B, is less than the previous connection that we've established. So from A to C, right? Or A to B, rather. So for instance, if this was a 5, so it was greater than the cost from A, well, that's a less efficient path, right? We don't want to put that into our routing table, so we ignore it. But in this example, it just happens to nicely work out that both solutions are better, so we're going to update our table respectively. And then we remove C from consideration, so we take that out. So going through it another step, we look at the costs to B and to D. The cost to B is 3, the cost to D is 4 from the beginning of our network, so we're going to move to B. So A, C, and B are in the consideration set. We're going to, because we've moved to B, we remove B from consideration, so we go ahead and add these dashes here, because we're no longer looking at it. To find a better route, we've already found the best route. And then, there we go. And then we add B into consideration for the local neighbors, right? So we update it with the total path, which is going to be 3. We put the neighbors in, the only one left to discover is D, and the cost is going to be 3, right? From B to D, right here, following this. So all that provided, we know that the cost, the initial cost of 3 and the updated cost from B to D is 3, right? So that's 6. 6 is not better than 4. So like earlier, I said the only reason we update this table is if we have a better solution. We do not have a better solution, so we persist the previous step from the previous step of the algorithm down to this level. And then remove B from consideration. And then because D is the only node left, we add D to our set. D is being considered, so we remove any possible changes from our routing table, and the algorithm is complete. And from this, we've discovered the best possible cost to get to any node in the network given every other node in the network, right? And the sort of cool bit is starting from A, if I want to get to C, I can look at my routing table and say, oh, you know, the way I get to C is by starting at A, and I'll go directly to C. Or if I want to get to D, I go to the very bottom and say, okay, I go to C, and then if I go to C, I go back to get back to A. This is sort of the route, right? So you can use this table to, from any node, get to any other node, starting at one node, right? So it's sort of a backtrace thing, where you start at the end and you work your way back to the front, and that's how you find the least path using Dijkstra's algorithm. And then we remove D from consideration. Kind of jumped ahead. There we go. So if we want the best path from D, we start off at the very bottom of our table for D, and then we move back to C, and then we look at the C node, and we move back to A. And that's how we get the least path there. So I'm not going to go through every single possible point with this example. It would take too much time. So we're just going to kind of walk through it together. If anyone's confused, please let me know. So this is a slightly more complex table. It's not immediately obvious what the best solution is. If you spend a couple of minutes staring at it, you could figure it out. But imagine that you extract this out to a much bigger network with lots more nodes. So we had A into consideration. So at this point, the current weight is 0. The nodes we haven't reached, the neighbors we haven't reached, are B, C, and E, with associated costs 11, 4, and 2. So we're going to update our table. To get to B, it's 11. To get to C, it's 4. To get to E, it's 2. And the other 2, it's infinity because we don't have a direct connection from node A. Selecting the least one would be E. So we add E into our network. Remove E from consideration because it's already been selected. It's part of our selection set. We look at E, updating it at the total cost of 2. Looking at the nodes not yet reached in our network, which would be C and F. And update with the local costs of 1 and 7. So we just add the initial cost to the local costs, and that's how you can update a table. Yet again, the choice from E to C is better than the choice from A to C, therefore the table gets updated. And then from F, well, we couldn't reach F before, now we can reach F, so we update the table correspondingly. And looking at that, the best... Oh, and then we propagate down the previous information that hasn't changed. So C is the best choice there, right, between 3 and 9. 3 is obviously smaller, so we pick C. Remove it from consideration, put it in to our local sort of nodes graph, update the total cost of 3, add the neighbors, add the associated cost, update our table, and there we can see it's 6, and we propagate down the information that hasn't changed. We put D into our network, and we remove D from consideration, right? So we put these guys back in. Put D into our local neighbors graph, update the total cost, put the neighbors of D in, and the local costs from D to those nodes. We check to see, okay, are you less than the current choices? And we propagate those choices to our total routing table. Looking at those two, F is the shortest one, so we put F into our set for consideration. We remove F from the total routing table. We put F into our local neighbors graph, update it with total cost to F. Put all of the neighbors of F that we haven't yet considered in our. I've been saying that we haven't yet considered. What I mean by that is we haven't previously put into our consideration set here. So the reason why only B gets added, even though F has a bunch of different connections to different nodes, is B is the only one that hasn't been put into our consideration tables. That's what I mean by hasn't been considered. And then we update the local cost. Sorry, this is it's an algorithm, so it just repeats itself over and over again. It's a better choice to get from B to F, so we update our table. We put B into our local routing table, and And now the table is complete, right? We filled out every single spot, and to figure out from A to get to any other node in the network, we can simply follow by looking at the bottom of each of these columns, and that gives us sort of the route. So if I want to get from A to F, I would take the route from A to D. We go the other way around. So we go from F to D, and then if we go to D, we go to C, so D to C, and then from C we go to E, and to E here, and then from E we go to A, right? So we take something like this, or that. So we kind of reverse it. After you calculate the route, you turn it back around, because we want to go from start to end, not end to start, right? That's how Dijkstra's works. It's relatively simple. Well, it's a little bit complex, but once you've gone over it a few times, it's a simple algorithm. And it's incredibly powerful to calculate all of the best routes from one node to any other node in the network. So here's sort of the alternative to Dijkstra's. It's the, if Dijkstra's is the monolithic centralized version of a routing algorithm, distance vector routing is the distributed version. So this is how people tend to do things nowadays with big, large distributed networks. It's a more localized cost problem. So, each router within a network has a table with the best distance from itself to any other node, right? And we periodically update these tables to reflect changes in the network based on some criteria, right? So we can make it more static. We talked about static and adaptive earlier. We can make it more static, where it updates less often, and it relies on the weights that are calculated at a particular time. So that may be at the beginning of a day, in the middle of traffic of a day, whatever the network engineer decides is the best, right? And it's not too complicated. It's a lot simpler than the previous one. So if we have some node I here, I is going to receive a table from node J saying, hey, the distance between myself and K, or the cost between myself and K is X, right? And I knows from something like link state routing or flooding, whatever it might be, that the cost from itself to J is Y, right? Just using localized costs. So because J propagated the cost X to node I can sort of, there we go, yeah. So because J propagated the cost from K is X, right? So from J to K, so this way is X. But it's sort of bidirectional, right? If I go this way, it's X. If I go that way, it's X. It doesn't really matter. It's just if we're trying to pass data from K to I, we go in this direction. So we propagate that idea to node I, and node I knows the cost from J to I. Then logically, I can sort of infer, okay, the cost from K to myself would be X plus Y. Or Y is the cost from myself to my local neighbor, and X is the cost from my neighbor to the node I'm interested in. And you can sort of see how that doesn't require having all the knowledge of a network and propagating a lot of packets back and forth. It's a very localized algorithm, which means it sort of efficiently calculates local routes. And we can use that by just following the best possible local route. You can then, most of the time, find the best possible total route throughout a network. So, yet again, complicated little graph, but it's not that bad. So we want to figure out what's the estimated delay from J to G. So J is right here in our network, and G is right here. So trying to get through that. And then this is the vectors containing the associated costs from J to each of its neighbors. So this one right here is from J to A. So we put A at the top here, right? From J to I, so we put I here. From J to H, so we put H there, and K as well. And really what this is this is the localized routing table from something like, yet again, lake state routing or flooding for node A. So it has from A to everything that A has a sense of. And that could be from propagated information from other nodes, right? I'm using that whole distance vector algorithm idea, where I figure out the cost from my neighbor to its neighbor, and then from that neighbor to its neighbor, from that neighbor to its neighbor, we can sort of go, okay, I have no idea from node J what the cost is to get to something like D, right? But I do know what it is from J to H, and H knows what it is from H to D, so we can sort of use that to guess, okay, well, here's my guess of what it would take to get from J to D. So in order to calculate this localized distance, we start off just picking the first one of our neighbors, right, A. So to get from A to G, right, we know that the localized cost from, where is it? Oh yeah. So we know the localized cost from ourselves to A is 8, right here. And then we know that from node A, the cost from itself to G is 18. And what we can do is, oh, whoops, I haven't updated. But what we can do is take the cost from ourselves to that node, and then from that node to the node we're interested in, and all we do, like earlier, is just add them together. And our guess of the cost from J to G following route A, it would be 26. And we don't yet update our routing table over here, right? We don't want to put it into, where is J? We don't yet put it into here. We want to wait until we've calculated all the possible neighbors, going through this one, this one, this one, and this one, all the possible routes we can take out of our node, in order to try and find what's the least one and then pick that, right? So we did the same thing again with I, so moving from this to this column, and we know the cost from ourselves to I would be, apparently it's 31. Oh no, 10. There we go. Yep. So there we go to 10. And we know the cost from I to G would be 31. So we just add 10 and 31 together, we get 40. And same logic again to get from through the H path. And then same thing for the K path. And then once we've totaled up these costs, oh actually, there we go. That's a much easier way to find the localized cost. But once we've totaled up the summation of the localized cost with respect to the cost from that node to the target node, we can sort of rank our best choices, and 18 is the best choice. So we're going to update our personalized routing table here to follow the path of H in order to get to our end node. So yeah, the smallest possible cost is selected, and we're going to follow that path. So there's positives and negatives to this, right? Positive, it's distributed, it's easy to update local changes in the network. So if one thing goes down or the cost between you and your direct neighbor is changed, but it's difficult to propagate big changes elsewhere in the network, right? So for instance, if back in this example, right? If I'm going from G and I wanted to follow this path here, it would be easy to figure out a change to A, but if B goes down, we're not going to figure that out for a few steps of this algorithm. And that's where the concept of count to infinity comes in. When you run the algorithm, and you get the information from your neighbors about what the costs from them to any other network any other node in the network is. What is it? If the cost goes down, and you want to select the least cost, right? So that propagates quickly. But when something goes down and the cost shoots to infinity in theory, right, because there's no link between that, so we represent that as infinity, it's going to take a while for you to figure that out. And we call the convergence time of a network is the time it takes for any particular node to figure out, okay, that link's gone down, that link's degraded, something's gone wrong. So the convergence time is the time it takes for any particular node to receive that information. And usually what we do is we look at all the nodes in the network and we say, this node has the worst possible convergence time, therefore the convergence time for the total network is the worst possible node, right? And that gets back into things like big O notation, right, where we look at the asymptotic runtime of a function. We want to find the worst possible scenario and map that out, because if we're winning on our worst possible scenario, then we'll be winning in the better and the medium cases, right? Oh, there we go. I forgot about this example. So this is sort of the example of the counter-infinity problem. So with good news, right? So to begin with, node A doesn't exist. It's fallen off the network, something's gone wrong. Some engineer somewhere has accidentally hit the power switch and turned off the machine. And we come back online. And the information, hey, A is online, propagates very quickly. So after one exchange, the cost from A to B, because there's some localized neighbor, is 1. And the cost from B to C gets updated, and from C to D, and from D to E. So very quickly, good news passes through our network, because we're always looking for the least cost. So because A cost is less than infinity, right, which would be what it's set to in the case that the node's down, that propagates quickly. But the other way around, where we start with a node A in the network, and it goes offline, and again, somebody screwed up and turned off the machine, that's going to take a while. So if initially the cost from A to B was 1, from A to C was 2, from A to D was 3, from A to E was 4, well, 1's going to go down, so that's going to go down to 0 or infinity, and then that's going to, so that's the beginning. There we go. And then we're going to begin to propagate. So B has no idea how to get to A, so B is going to look to C and say, what's your cost to get to A? And C's cost to get to A was probably through, it took a weight of 2. But because C can't query A anymore, it's going to update its value by 1. And B is going to be 2 plus 1, so it's going to propagate here. And then so that sort of local process repeats again, and it repeats again, and it repeats again, and again, and it gets worse and worse and worse and worse, until eventually, fingers crossed, we get to, hey, A is not connected, all of these will be infinity, which is what we get to right now. That takes a really long time, it's inefficient, it's a waste of network resources, so it's not the best with responding to bad news, right? And this is where you might have asked from earlier, distance vector routing. This is a much simpler algorithm than Dijkstra. Why would we ever use Dijkstra when we have this nice, elegant, easy algorithm? It's because of things like this, right? If we're watching a network begin to degrade, we're watching the routing table of a particular set of nodes and their connection to something like a node A begin to count upwards, we could run something like Dijkstra to check, hey, has something gone wrong? Do I need to make a big change? Or we could just put some sort of simple heuristic in there that says, hey, if we begin to climb over n number of seconds, then just set it to infinity, skip the count to infinity problem. Yeah. Take a break. Wait, now? Yeah. Okay, right, we're going to take a break.
Don't mind sort of finishing a bit too early. I mean, it's good for them to sort of take a break as well, but you're doing great.
Okay.
And it gives you an opportunity to catch your breath.
Catch your breath, yeah.
I'll stop this for a bit.
Okay, welcome back everyone. I'll let you know the first half and the second half of this lecture are not going to be of equal length. We're almost done, so don't worry. If you're falling asleep, you'll be free soon. So we're going to finish up talking about routing methods analysis. So how do we make these decisions about what routing methods to use? Why do we use one over another? What scenarios should you pick Dijkstra's versus link state versus doing something like just a bunch of flooding algorithms? So there's this concept of least hop route, which I think I accidentally mentioned way at the very beginning of the lecture. And it's often, not often, but sometimes when you're running a routing algorithm, you have criteria that exist beyond just the best efficient link, right? You might want to limit the number of nodes you pass your data through or your message through. This might be for security reasons, so you don't have to lock it down quite as hard, or you don't trust as many intermediary nodes, or just you don't want to have your packet stamped with a bunch of intermediary, what's it called? Completely blanking on what it's called. Like hash code values, right? So so effectively, as it passes through each node in a network, the node is represented by a router, which is just a machine, and it's going to put its own unique sequence number on that node, just to let all other routers who receive information from packets in the network know when it hit me, it was the 153rd packet to hit me in this hour or this day. So you might want to limit that, right? It depends on sort of the use case, but there are reasons why you want to pick the least number of hops. And the way you calculate that really easily is you use Dijkstra's algorithm and just set the distance or the cost from each intermediary node to 1, right? So when you run the algorithm, that's just going to pick the logically shortest path to take. And then same thing with distance vector routing. It's just going to pick the first one to be found at each destination. So looking on your routing table to pick the first node. And that will get you the least number of hops. So Dijkstra's algorithm, yet again, it's called the shortest path algorithm. When you see shortest path and Dijkstra's, it's the same thing. So the strengths are on a smaller network. So if you have just a few nodes, something in the span of 50 to 100 maybe, this is fairly simple to calculate. Not by hand, that would be extremely difficult. But using a computer, it would run very quickly. And the big advantage to this, right, is you could have a centralized repository of all the information for all the best possible paths for any particular node. So you could just tell all the nodes in your network, run Dijkstra's algorithm, and then if you want to get to any other node in the network, you have the best possible path sitting there, ready to go. The sort of big weakness is if we go back to Dijkstra's, we compare that to distance vector, right? Dijkstra's is a far more complex algorithm. I think it's like big O of n log n or something like that, or n squared maybe. But it's more computationally intensive, right? Because we have to have knowledge of all the possible nodes in a network. We're not just considering our local neighbors, right? When we went back to distance vector routing, with node J, we just looked at the local neighbors of A, I, K, and there was another one I can't remember. And we only have to consider those local neighbors, right? Because those neighbors have information about all the other hops to other nodes in the network, and we can base our approach off of what our neighbors think is the best route, and then their neighbors think is the best route, right? So it's sort of more distributed. Should have waited until I got to the distance vector side, but yeah, distance vector routing is it's a distributed algorithm, so it's easier to run on massive, huge networks. I'm talking about thousands and thousands of nodes, where it's just not feasible to do Dijkstra's, right? Because if you think about it, right, if I have 10,000 nodes in a network, so I've say I'm representing all the nodes in Tyne and Weir, right, and I want to connect everything together. If I wanted to do Dijkstra's algorithm, I would have to have I'd have to have a 10,000 by 10,000 size matrix stored at every single node. And that might be feasible for some of the more powerful ones, but if my friend George has a Raspberry Pi that he's connected to the network, and he wants it to be used as an intermediary node in the network, it's not feasible for him to update that table every single step, right? But you could with distance vector routing. And this is crucial for technologies like cloud computing, IoT, things where edge computing, right? Things where distributed computing is becoming more and more useful. So sort of a combination of these two in the real world is sort of the practical way to do things, right? Yeah, local costs can be easily detected, and local positive changes are easy to detect. It does take a while to find sort of distant costs to routes in a network, especially if I go from A to J, J to K, K to I, and the connection from K to I degrades, it's going to take a while for node A to figure out that further connection has degraded. So yeah, these are sort of the benefits and detriments of each algorithm. And I recommend sort of studying these two slides later on, or just giving them another glance over. Okay, so we get to the fun stuff. So, as Pedro mentioned earlier, I'm doing research into load shedding with respect to stream processing platforms. But load shedding is a concept that exists in networking in general. It's been around for a very long time. I'm just trying to apply it to a slightly new use case and doing what I hope is a novel and clever sort of iteration on that process. But here's sort of the original logic behind things like load shedding. It gets into the concept of congestion control. So I mentioned congestion earlier, very briefly, and I said that we'd talk about it later. Here's what we're talking about it. And congestion is where, in theory, in a perfect world, if we increase the number of packets that are entering our system, and the capacity of our network is this line here, then the amount of packets able to be processed per second, so packets per second, it's called offered load. We'll get to that in a second. It would just linearly increase until we hit our max, and then it would plateau. So that would be you know, if this world was a perfect system and everything worked exactly as it should, that should be what happens, right? But it's not, and that's because of this concept of congestion. So the number of packets that actually enter the system versus the number that our system can handle, it begins to increase linearly. That part's the same. Then we hit some point where congestion begins to occur, and this is packets sort of backing up on our system. So sort of the general definition of congestion is just when too many packets are present in the subnet, performance degrades. So performance degrading, right? That would be the length of time between two networks increasing. What does that actually mean? How does that actually work in a network? Usually it's because of things like concurrency control. So if we have buffering at a particular router. So buffering would be if I have too many packets of data that hit one router at a particular time. It's going to, we don't want to throw that data away, right? And we can only forward so many packets per second. So we might begin to store those packets in what's called a buffer, which is just a localized store at that router. We have what's called an input buffer and an output buffer, usually. If it's a dumb router, a very simple router, something designed 30, 40 years ago, you might not have any buffers. It might just be a fire and forget sort of situation. But nowadays, we tend to have buffers on these routers. And your input buffer would be, okay, it's taking me a while to process this data and send it to output. So I'm going to begin to store things before it hits the router, so sort of at the beginning. And your output router would be, okay, the actual outputting network is telling me it can't take any more data. So I'm going to begin to store things that I've already processed that are ready to go. I just need to wait for the network to clear up a little bit. And as you can imagine, right, usually your output buffer fills first, and then your input buffer fills, and then the output buffer of the next node fills up, and then the input buffer fills, and that's congestion. And it's not a good thing. Usually this can lead to sort of the death of a network. So sort of network engineers, this is our main job, right? Is trying to figure out how do we avoid this catastrophic situation where congestion causes the whole system to collapse and things go very poorly. And we have a lot of methods like TCP slow start and quick start, which is, I think it's called quick start, that we can use to quickly recover our systems. I think we'll be talking about that in the next lecture, which is the transport layer. There we go. So I mentioned offered load. Offered load being the number of packets per second that we can take into our system. And here's a nice little maths equation. I went ahead and I threw the citation if anybody's interested. It's Introduction to Queuing Theory by Robert Cooper. Very good little book. The type font is pretty bad. I think it was before the whole Xerox Bell Labs fight. So if you're okay reading a really crappy type font, it's a good book to read. Anyway, we can represent it with a mathematical formula called Little's theorem, where L represents the mean number of packets that are present in the system. We could think about this as the offered load, or the amount of packets that we can actually handle in our system. It's the load our system offers to the rest of the network, hence offered load. We have lambda, which represents the arrival rate of packets. So it's the number of packets per second entering our system. So hitting our input buffer and then passing into our router. And then we have W, which represents the mean waiting time of packets. So how long does it take for that packet to pass through our router and hit our output buffer? So not necessarily hit our network, because that's dependent on whether or not the network can handle new packets of information. It's how long does it take for the packet to hit the input buffer, pass through a router, and hit the output buffer? So that's W. It's not the total looking at the buffering time as well, just looking at how long it takes to get through that router. And there's sort of an unfortunate consequence of all of this, which is the offered load of any system is directly tied to the amount of computation present, or in modern terms, the level of operator parallelism within a network. And who talked about parallelism? No. Okay, that's fine. So when we have multiple machines that are trying to do the same thing at a time, what you might do, if I have two computers that are both attempting to forward packets to one output node, right? Because they're doing the exact same task, they're taking the same types of input packets and they're outputting to the same output packet, within our graph diagram of our network, we would represent them as a single node because they're doing the same job. But it's twice the amount of computation as a single computer, right? So we call the amount of computers doing the same task within a network, the parallelism of that operator, the parallelism of that node. So a parallelism of 1, in a very simple case, would be there's one machine on each router. When you look at your graph, there's only one machine doing those tasks, right? And one of the ways we can handle increases in network traffic would be to modify the path, right? So if one node's being hit by too much traffic, we might try and split our traffic around that node to sort of ease off the amount of computation the node has to do. But another way would be to throw more computing power at it, right? Would be to spin up another computer with the same configurations and say, your job is to help the original machine deal with the routing configuration, right? But this gets back to the level of offered load, so the amount of load that any particular node can process is directly tied to that parallelism, the amount of computing power that we have. And that's fairly logical, right? It makes sense to say your machine is only as powerful as the amount of power your machine has, right? That's basically what this says. And we'll get later into some more recent theory about how we view this and what we're trying to do to fix this problem. Because sort of the end consequence, right, is as computer systems to get bigger and bigger and more complex, we need to throw a higher level of parallelism at those networks in order to accommodate the traffic. So for instance, Facebook, right, that Facebook gets millions and millions and millions of message requests every single day. It has to handle very complex, you don't want to accidentally send a message and for that to be received by the incorrect person. It needs to be handled in the correct way. So really the only way to deal with that is to throw more computing power at it, which is why I think the Facebook Altoona Center is one of the biggest computing centers in the United States and consumes gigawatts and gigawatts, and I don't know what the bigger value of gigawatt would be, but of power every single day. And as we're becoming a more energy scarce world, we need to be able to sort of deal with this issue. This is sort of like an end boss crisis, if that makes sense. So if anybody can figure this out, please let me know, because that would be huge. So a couple of different approaches. I sort of mentioned them a couple of seconds ago. So we can increase the amount of resources or decrease them, and that's called auto-scaling. That gets back to that whole level of like increasing the parallelism or decreasing the parallelism. It's called auto-scaling. There's a bunch of good papers on this. You could read DS2, which was published by Matthew Forshaw, the professor here at this university. And AWS and what's it called? There's the Google one and Microsoft Azure. These are 3 cloud computing platforms. One of the big sales for all of these companies is that you don't have to have an engineer sitting there manually changing the number of computers that are behind each process. They have very complex algorithms that do this auto-scaling for you from scratch. And you don't have to deal with it, right? You just set it off and let it run and let it do its thing. Yet again, that gets back to more and more computing powers being thrown behind these big tasks. People are writing code less efficiently because they know they don't have to write efficient code anymore. They just, fire and forget sort of situation. I'm not a fan of autoscaling, but it is a solution. You could just build a network that's well provisioned to deal with the amount of traffic. So for instance, that would work for a situation like Newcastle's campus, right? We're going to have a max amount of network traffic that you could probably accommodate just based on a number of students, average number of messages, amount of staff, things like that, right? And you really wouldn't need to allocate that much more. Maybe the amount that you'd estimate plus 10% would be a good way to set up a well-provisioned network that wouldn't have to change very often. You can do traffic-aware routing, which is where we, yet again, if we have one network that's really overburdened, we could split traffic around that network in order to allow the network to have less data, means it has to process less stuff, means it can recover more easily. Or we could do something called traffic shaping, which we're about to get into, which is regulating the amount of traffic that passes through any node in a network. And it adds a higher overhead for that particular node, but it allows downstream nodes a better rate of information or controls the amount of information that's being passed through. And we'll get into that in a sec. So one of them is called the leaky bucket algorithm. This is part of traffic shaping. And computer science, it's a relatively exoteric degree, so we like to try and connect things to real-world stuff as much as possible. So you can sort of imagine it like you have a leaky bucket, right? You've got a bucket with a little hole in the bottom. And at the beginning, we just have this tap is turned on full blast. And it's adding a whole bunch of water into our bucket. Our bucket is filling. But I don't know, we have a delicate flower out here at the bottom. And we don't want to destroy the flower with this fast pace of water. So instead, we put a bucket in the way with a little leak in the bottom that slowly drips water out so we don't accidentally destroy our flower. And that's our network, right? We've got a really bursty or a high throughput source node that's sending a lot of data downstream. So we're collecting that data and we're doing what's called source rate limiting. So we're limiting the rate at which data is coming out of our source node by putting an artificial buffer, like a really big buffer, to sort of limit how much data gets passed downstream. And usually that's because we have an estimation of how much data our downstream network can process, right? The offered load of our downstream network. And we don't want to exceed that. So we stick this little leaky bucket interface here, and it sort of eliminates this burstiness. So we get a burst here, we get a burst there, and it brings it out as a regulated flow of the output. So yeah, it smooths the burstiness from the source rate and reduces chances of congestion. Because congestion really only occurs when we've exceeded the buffers. So if we've limited the rate to something our system can actually handle, then we're not going to exceed our buffers, right? So another way to deal with this is called the token bucket, where we have this sort of bucket here. It's just, yet again, it's just a buffer, it's just a big buffer, where it's going to sit there and intake packets, and it's going to generate tokens. And these tokens are usually generated at a set interval, or maybe you have some flag that your downstream network has set that says, hey, wait, right? And it's going to not generate any tokens, and then it's going to say proceed, and it will start to generate tokens again. And it's effectively one token per piece of data. So if I want to send something to the output buffer, we'd wait for the tokens to be generated in the bucket, following yet again some sort of logic, and then we can pass those to the output stream. So it usually creates tokens at a constant rate based on some clock. So that might be Lamport time or clock time. If you guys have done distributed computing, that's that concept. And yeah, it's one token per piece of data. So the data waits in the bucket, it waits in our buffer until a token's been generated, and then we output it. Now, this algorithm also allows for sort of large bursty streams, right? When it comes to our downstream network, if we say wait and then proceed, during that proceed step, we might send a whole bunch of data all at once. And that could be bad. So usually what we'll end up doing is we'll stick a token bucket upstream sort of first, and then directly after that token bucket, we'll put a leaky bucket. So the token bucket deals with storing large amounts of data from an upstream host and getting ready to output like a certain amount at a time. And then the leaky bucket deals with regulating that flow into something that our network can actually handle. And a combination of those two things is a great way to do network shaping. And there's a bunch of other ways to do it, but these are sort of the simple, easy ways to deal with network shaping and shaping the rate and the flow of data through a network. And the last bit. So I mentioned earlier my research is doing, I'm looking into load shedding with respect to stream processing engines. So this is load shedding. And it's sort of a competitor. I don't want to say a competitor. It's an alternative way to do the concept of autoscaling. Right? So autoscaling is we've run out of computational resources for a particular operator, whether that be routing, whether that be doing some sort of processing, whatever it is. And we throw more computation at it, right? Or we have too much computation and we're just wasting electricity, power, money. So we start to shut computers down. What you'll find with highly reactive networks, right, where people are kind of logging on and off and sending messages at irregular times, is that we'll get a lot of variation within our network. So big providers like Amazon, Google, Facebook, Twitter, etc., will allocate significantly more resources than they actually need because they want to accommodate for those changes within the network, right? The sort of dynamicness of how people interact with the internet. Often, you don't actually need to allocate that amount of resources, and what you'll see is there's a significant amount of idle time on these massive computer farms. So instead of turning on more resources, what you could do is selectively throw away packets, which sounds crazy, right? Like, why would I throw away data coming through my network? Isn't the whole point of a network to forward on data? Why would I throw things away? Well, for situations like IMing, right, instant messaging or something on like WeChat, right, you wouldn't want to do that because you want your messages from your friends. But say I have a sensor on a wind farm off the coast of the UK, right, and that sensor controls the torque on a bearing in this massive windmill, and I need to get a regular output of that to know, should I be fixing the windmill? Does the windmill need repairs? And there's a bunch of these sensors all across a windmill. There's a bunch of these windmills all across this little wind farm, and there's a bunch of these wind farms all across the UK. That's terabytes and terabytes of data every single day. And depending on the sort of fine gradeness of your data, you might be getting an input every couple of minutes, right? Which leaves sort of these companies to have to process that downstream or be able to store it, deal with the network traffic. Like, it's intense. And this is a real-world use case. It's something we're looking into here in Newcastle. How do you deal with that? Yeah, load shedding is just the process of throwing things away as they come in and making an intelligent decision about how to do that. And there's sort of two big approaches. There's the wine approach and the milk approach. These just make things simple, right? The wine approach is older packets of data are more useful or relevant to us. So you want to maintain those packets. So when new packets come in and we can't handle them, we throw away the new packets. We keep the old packets because they have some sort of information that's useful, and we throw away the new ones. Probably should have thought of an example, but I can't think of it on the top of my head. I will think of something later. And the milk approach is just newest packet. It's more up to date. It's more useful. We want to keep that instead. So for instance, financial data down in London or in New York or wherever else financial stuff happens. You want the most up-to-date information about what the stocks are, right? So the milk approach would be what you do. You discard old packets to make room for new packets. And this logic can be remarkably simple. It could be just throw away every other packet. It could be look at the difference between two packets and throw them away if they are too similar, right? There's a bunch of different ways to do load shedding. But yeah, that's sort of the alternative to how do you deal with network traffic. We've got sort of this idea of traffic shaping, and we have the idea of throwing more resources at it. We have the idea of throwing away data if we can't accommodate it. And I believe that's it. So thank you very much for your attention. If you have any questions, feel free to ask me or cut your hair.
As you've just seen, Ian is a pro, he really knows his stuff. So it's been a pleasure listening to him, and you'll get the chance to hear from him again on Thursday and in 2 of the tutorials, so please come for those and try to make the most out of it. In terms of, there's another couple of things I wanted to cover. Right, so the next two lectures we have on Wednesday, we're continuing with the network layer. So routing is relevant to the network layer. We're studying the IP protocol on Wednesday. And then on Thursday, Ian will be with you to talk about the transport layer. So, and in terms of what is relevant for the exam, I think today you're expected to know how to work through those different algorithms that Ian explained to you, namely the Dijkstra's algorithm and the distance vector algorithm. So we'll have a couple of examples in the tutorial sections, and as well for the coursework for you to study and prepare for the exam. Also reviewing the pros and cons of each algorithm is also going to be very helpful for the exam. So I think that sums it up for today. Thank you for coming, and hopefully see you again on Wednesday. All right, cheers.